Welcome back, everyone. Today, we've got an explainer that's honestly going to mess with your head a little bit. We're diving into a deeply thought-provoking paper by João Carlos Holland de Barcelos called Decreasing Universe Theory, Cosmic Time Dilation, and the SN1A Explosion. If you've ever looked up at the night sky and just accepted the idea of an expanding universe, well, prepare to have your perspective completely flipped upside down. Because this paper poses a totally mind-bending question. What if the universe isn't actually expanding at all? What if, instead, our local rulers, our planets, and our very own bodies are just continuously shrinking? I know, it sounds a lot like science fiction, right? But Barcelos argues this elegantly using fundamental physics. The basic premise is that the expanding cosmos is essentially an optical illusion. The room only appears to be getting bigger because we, the observers inside it, are getting smaller. Here is how we're going to break this all down today. First, we'll look at the current mysteries of the universe. Then, we'll introduce the decreasing universe theory itself. After that, we'll tackle the illusion of dark matter, followed by the effect on time, cosmic clocks, specifically supernovae SN1A, and finally, we'll compare all of this to general relativity.
All right, let's jump right into part one, Mysteries of the Universe, taking a look at standard cosmology. So right now, standard physics kind of leans on these massive invisible placeholders to make the math work. We've got dark energy, which physicists proposed simply because galaxies seem to be accelerating away from us. And then we have dark matter, a theoretical idea needed because stars at the outer edges of galaxies are moving way faster than visible gravity should allow. Basically, the current equations fall apart without them. But Barcelos asks a huge question. What if these aren't invisible forces at all, but just complete misinterpretations of the data?
Which brings us to part two, the decreasing universe, or the DUT hypothesis. The core idea here proposes that gravitational fields cause space, and literally everything inside that space, to constantly contract. To explain this, Barcelos splits observers into two categories. First, you have the co-moving observer. Imagine someone way out in deep sidereal space where gravity is practically zero. They are not shrinking. Second, you have the proper observer. That's us, sitting inside a gravity well like Earth, and we are continuously shrinking. Keeping that difference in mind is absolutely crucial for the rest of this theory. Now you're probably wondering, if we're shrinking, why don't we notice it? Well, it's incredibly slow. The paper estimates the contraction rate on Earth at about 7% for every 1 billion years, because you, your ruler, the planet, and everything around you are all shrinking at the exact same proportional rate. You don't feel a thing. But when you look out into the vastness of space at objects that emitted light millions of years ago, this very slow shrinking effect creates some massive optical illusions.
Let's move on to part three, the dark matter illusion. It really all comes down to perspective.
Normally, astrophysicists look at redshift, which is light stretching into redder wavelengths, and say, yep, that proves the universe is expanding. But DUT flips this completely. It says redshift happens because our measuring tools are shrinking while that light is traveling to us. The theory points to three things driving this. First, mass. More massive galaxies shrink faster, altering the light they emit. Second, age. Older galaxies have just been shrinking longer. And third, distance. The longer a photon takes to get here, the smaller our rulers have become by the time it arrives, so we measure the incoming wavelength as much larger, giving us a redshift.
And here's how it accounts for the dark matter illusion. Stars on the outer edge of a galaxy experience less gravity than stars near the center. Because they have less gravity, DUT says they shrink slower. So they emit light with naturally longer wavelengths. When that specific light finally hits our telescopes on Earth, we misinterpret those longer wavelengths as extremely high orbital speeds. We literally invent dark matter to explain this phantom speed, but DUT argues it's just a trick played on us by our varying rates of contraction. Okay, part four, the effect on time. Because if gravity shrinks our rulers, what does it do to our clocks? Think about how we actually define time. The modern definition of a second is fundamentally tied to a physical distance. It's the duration of over 9 billion periods of radiation from a cesium-133 atom. Since a period of radiation is a physical wavelength distance, and DUT states that gravity shrinks all physical distances, then our very measurement of time is completely tangled up with our shrinking space. Here is where things get truly wild. The speed of light is invariant. It's a universal constant. But because our physical meters are getting shorter, light crosses them faster from our local point of view. This means our clock here on Earth, the proper observer's clock, is actually ticking faster relative to that stationary observer out in deep, gravity-free space. We don't notice our physical processes speeding up because our local clocks are speeding up right alongside them. Let's look at the evidence for this in Part 5, supernovae SN1A, which act as our cosmic clocks.
How do we test a theory like this? We look at perfectly uniform exploding stars. Imagine a supernova explosion as a giant cosmic tic-tac. Tick when it starts, tack when it finishes. That light takes millions of years to reach us. Under the decreasing universe theory, during those millions of years, our clocks here on Earth have been continuously shrinking and ticking faster and faster. So when that ancient, slower light finally gets here, our fast clocks measure it, making the distant explosion look stretched out or dilated over a longer period of time.
This leads us to a pretty incredible mathematical conclusion. The time we measure on Earth, TT, equals the original time of the event, T0, multiplied by z plus 1, where z is the redshift factor. Why does this matter? Because real-world astronomical data conclusively shows that the time of distant supernova explosions is in fact stretched by a factor of 1 plus z. Standard cosmology really struggles to explain this cleanly, but the continuous shrinking effects of DUT, it maps to the observed data perfectly.
Finally, Part 6, general relativity versus DUT. Let's see how this stacks up against Einstein. Comparing these two really highlights a fundamental philosophical difference in physics. Under Einstein's general relativity, time dilation is an instantaneous, non-cumulative effect based entirely on your local gravitational potential. It doesn't build up over time. But with the decreasing universe theory, time dilation is a continuous evolution. It's a cumulative effect that builds up over millions and millions of years of cosmic time as your frame constantly shrinks. The author of the paper actually ran the math to see when these two effects cross paths. He wanted to know how long it takes for DUT's cumulative time dilation to match the localized relativistic time dilation predicted by Einstein right here on the surface of the Earth. The answer? Exactly 10 years. After just a single decade, the cumulative cosmic effect of our shrinking universe perfectly compensates for the instantaneous local effect of gravity. It is an absolutely elegant mathematical bridge between the cosmic scale and our local scale. Which brings us to our final provocative thought. Next time you look up at the stars or check out images from a deep space telescope, you have to ask yourself, are the biggest mysteries of the cosmos really a matter of invisible, undetectable dark forces pulling galaxies apart? Or are they simply an optical illusion created by the fact that our own planetary rulers and our own clocks are continuously shrinking? It's a profound shift in perspective and a great reminder to always question the lens through which we view reality. Thanks for joining me for this explainer, everyone. Keep asking big questions, and I'll catch you in the next one.